Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we will be covering limit laws and how to solve basic limits. So first, I'm going to go through a set of 11 limit laws. Basically, these will tell you how we can use these laws or a combination of them to solve problems involving limits. So the first law that we're going to go over is the addition of two functions within a limit. So if we have a limit, for now we're going to ignore this like x approaches like any value right here. We're just going to write limit, meaning that x can approach absolutely anything. So if we have a limit of f of x plus g of x, we can break this down into the limit of f of x plus the limit of g of x. Now the second law is pretty similar. It is the subtraction of two functions within a limit, and like you could guess, all we're going to do is we are going to subtract the two limits. Now the third law deals with the multiplication of a function within a limit. So if we have a function being multiplied by this constant called c, what we can do with this is we can kind of bring it outside of the limit, so we can multiply the entire limit by c. Now we just dealt with the multiplication of a function by a constant. Now what if we have something like where we have two functions being multiplied together within the limit? Well, what we can do is almost like the addition one. We can just multiply the two limits. And like you could have guessed, the fifth one, if we just did multiplication, we are likely to do division. So if we have f of x being divided by g of x and we're trying to take the limit of this whole thing, we can split this up by taking the limit of the top function and dividing it by the limit of the bottom function. And we can only do this provided that the limit of g of x is not equal to 0. Otherwise we're going to get an error right here because we can't be dividing by 0. So the sixth law comes from a limit, like the function of the limit being put to the power of, let's say, n. What we can do is kind of similar to the multiplication one, is we can change this and instead put the entire limit to the power of n. So as you can see, before only f of x was being brought up to the power of n, but when we want to simplify it using this limit law, we can bring this entire limit inside the bracket and put it up to the power of n. So these first six laws we were dealing with, I told you that we were going to ignore this like x approaches whatever value, but now for the remaining ones, it will appear, and I'll show you exactly why. So these next few laws are really useful for actually solving the limit itself. These first six kind of give us a way to break down the problem that we have to essentially use these next like 4 or 5 that are going to come, actually 5, because the list will go up to 11. So the next 5 will tell us how we can actually solve the limit, how we can compute the limit, whereas the first 6 told us how we can kind of simplify the limit. So the seventh one is pretty easy. If we have the limit as x approaches any value of a, if we have it of a constant, so this c, it's not a variable like x, this c is going to be constant, so it'll be like the limit of 2. This will always equal to c, no matter what a is in this case. It will always equal c. So for example, if we have the limit as x approaches 2 of, let's say, the constant 5, this will always equal 5. Because if we think about it graphically, what this is just a graph like this, and we're saying, okay, well, we have this function right here which is just 5, and let's say 5 is somewhere up here. We have this vertical line, we have this vertical line of y equals 5, right? And then we're saying, okay, let's find the limit as x approaches 2, which could be somewhere here. Well, we're not really moving anywhere with the y value, we're staying at 5. So regardless of what x value we're going to choose to find the limit of, the value of the function will always stay at 5. So that's why the limit of any constant will always be just the constant itself, regardless of what x value we're going to approach. So now 8 looks a little bit similar to 7. However, the key difference is that we're not using a constant anymore. We're just using the variable x. So if we have the limit of the function x as x approaches a, this will always equal to a. And again, I'll show you a graphical reason as to why that is. So we have this function that we're dealing with right here, which is just x. The function is y equals x, which is the one that I've graphed right here. And essentially we're saying, okay, so as x approaches a, let's say a is right here. Let's say this is the x value called a. What value is this going to approach? Well, if we plug this value into our function, we get y equals a. So the y value at x equals a is also going to be a. And we could see that this is true for any a that we choose. If we choose an a to be here, plug it in, we're still going to get a value of a down here. So because this line right here, y equals x, is like a one-to-one function, it takes your x, it's called the identity function. It basically, it's the identity function of r squared. So it will take your x coordinate and it will give you that same x coordinate back. So if we look at this line and we try to go to x equals 1, well, the value at x equals 1 is 1. If we go to x equals 100, the y value of x equals 100 is also 100. So we can plug in whatever value of a we want here, and essentially we will be approaching this value of a. So that's why this limit is always going to equal to a itself. Now, law number 9 deals with a function to an exponent. So if we have the limit as x approaches a of x to the power of n can be anything, and obviously this right here is now our function. This will always equal to a to the n. And we can kind of see why later, but essentially all we're doing is we're substituting the value of a into the value of x. That's kind of what we've been doing this entire time for these past few examples right here. We take whatever value we're approaching and we plug it into our function, and then that is the limit. And the reason we can do this right here, we can plug it into our function, is because these functions are continuous. There's no need to like check if there's like any breaks in the function. We know that a raised to any exponent will either go something like this. Let's draw that a little bit better. Like this if it's an odd power, or it will be like this if it's an even power. So there's no discontinuities in these graphs. So we can just plug in the x value that we're approaching, and essentially it will give us the exact y value that we're going to be approaching at that x value. Now for law number 10, again, it's very similar. We have the limit as x approaches a of the nth root of x, and like I said, we know that this also will be a continuous function, so this will be equal to the nth root of a. Again, all we're doing is we're taking this x value that we're approaching and we're simply plugging it into our function, which is right here, because we know that the function is continuous. And we know when we're talking about a limit, we're thinking about the value that we're approaching on the graph. Visually, that's what we're doing. So algebraically, what that means is we can just plug in this x value actually into our function, and we should get the y value that it's approaching. Now, the last law, the 11th law, is if we have a continuous function under our root. So we have something like limit as, actually it doesn't matter what x approaches in this case, but if we have a function under our root, this will evaluate to the nth root of the limit of f of x. And I apologize, I did mention that the next, when I started at 7, I did mention that the next 5 will help us actually evaluate the limit, but this, the 11th one right here, is kind of an outlier. It does not, it helps us simplify the limit like the first 6 did. So it should be realistically grouped up there. My apologies, I put it onto the bottom over here. But these 4 right here, if I zoom out, these 4 help us actually evaluate what the limit will be. So it's not a simplification of like the equation that we're given, it actually helps us like evaluate it. So these 4 are extremely useful. Now moving on to direct substitution. I kind of went over it with these four limits right here. Essentially what we do is if we have this function, in this case I called it f, and it's a polynomial or a rational, meaning that it is continuous, and a is in the domain, that's like the key quality here, that a has to be in the domain of f, then we can simply just plug in the a value that we are looking for into our function, and that's how we can evaluate our limit. So it's pretty easy. Now the complicated part is when a is no longer in our domain and we have to kind of modify the function. But let's start off with a very simple example of how we can apply this direct substitution as well as these limit laws to a very, very simple problem. So let's look at this example right here, and we are given this problem to find the limit of 4x squared minus 2x minus 5 as x approaches 2. So we can see that we could just plug the limit in, and if you kind of wanted a shortcut, that's probably what you would do, but a good exercise is to go through our limit laws and kind of evaluate it one by one. So the first thing we notice is that it is a subtraction of these functions. So if we go back to our limits, we can apply number 2 to this and kind of simplify the way our limit looks. So let's do that now. So now that we've broken down this limit, we can see that we get 3 simpler limits. And now, again, we can just plug x equals 2 into any of these because they are polynomials and they do categorize like under this direct substitution, because 2 is within these 3 functions domains. So we could just plug it in, but let's expand and kind of work off these limit laws that we were taught. So what we can see here is that, again, we have a function being multiplied by a constant, and likewise here. So if we go back up to our laws, we can see that number 3 right here deals with that. So we're going to use this law right here to further simplify this limit. For this last piece right here, technically we could say that it is 5 times x to the 0, but I don't really want to get into that, so I just left it as a constant for simplicity. So now finally we have these bare bone functions, and now let's go back up to our limit laws and figure out which laws we can now apply to simplify our functions. So let's look at this first one right here, this 4 times the limit of x squared. If we go up and look at law number 9 right here, we deal with limits of this variable x getting put up to a power of n. In this case, n is 2. And what this law is telling us is that we can basically just substitute a in for x, and that will be our limit. So let's do that now. We can take 4, and then we are going to plug in 2 for x, and that is what the limit is going to evaluate to. So I'm going to do that now. Now moving on to the second limit right here, we can see that it's just the limit of just the variable x, and this corresponds with law number 8. So we're going to follow this law and say that this limit of just x is equal to a, meaning that we can just plug a into x, and that is what the limit will evaluate to. So I'm going to do that now. And lastly, we have this right here, which is the limit of a constant. And if we go back up, law number 7 deals with it right here. It just says that the limit of a constant, regardless of what a it approaches, is still going to be equal to that constant. So now the limit, this limit right here, will just be equal to this constant. So let's evaluate that now. And now, as you can see, we've gotten rid of these complicated limits and we're just left with bare numbers, and we can do this arithmetic and just find the answer easily. Now, if we were to look at a line like here, this very closely resembles what we have up here, essentially with just x for 2 substituted in for x. And like I said in the beginning of this example, we don't need to go through all these steps right here. This is too many steps to solve this simple limit. And all we should be doing is realizing that this whole function that we started off with is a polynomial function, and we can use this direct substitution rule because it is a polynomial and just plug in our a value of 2 into the function and evaluate the limit a lot simpler. So now let's take a look at an example that's a little bit different. Like I said in the previous example, that direct substitution was probably the best way to go about it, but now let's try it now. We are given this limit of this complicated function, and we are asked to compute this limit as x approaches 0. So let's see if we can directly substitute, right? We can plug in 0 right now for all the x's. However, we will quickly come to realize that we're going to be trying to do a division by 0, which is not allowed in math. So we quickly see that 0 is not part of the function's domain, so we cannot do direct substitution immediately. Instead, what we're going to have to do is a little bit of manipulation to this right here, to the top, the numerator of this function, and I will show you how that is done. So we start off and we do something, I'm pretty sure it's called rationalization, but we are going to multiply by the inverse of this numerator right here. Not necessarily the inverse, but I call it the inverse. It's going to have the opposite sign right here. So I'll show you what I mean by that. We're going to start off with the original function. I'm going to ignore writing the limit just because it's kind of a nuisance, but I'll bring it in later. So we start off with the square root of x squared plus 9 and minus 3 over x squared. Now what I meant by that is that we're going to be multiplying by the root of x squared plus 9 plus 3. So it's just the opposite sign. And we want to divide by the same thing, because doing this operation right here, we know that any value divided by itself is 1. So technically, we're not modifying the initial function because we're just multiplying it by 1 essentially. So this is a little trick that you can use. It'll help us simplify the function, and we'll actually be able to compute a limit in the end. So if we go on to simplify, we can notice that the top right here, the top of this multiplication right here, we can notice that this is the difference of squares. You could like multiply, like distribute like this, but it's kind of tedious, and I can start to see that this is a difference of squares because we know that like a squared minus b squared will equal to a minus b, a plus b. So essentially we can see that this right here is right here, and this right here is right here. So we know it'll evaluate to this. This is a formula you should have learned probably in like high school or something, but it's pretty common and it's used a decent amount. So I'm going to simplify the top by squaring a, which in this case is the square root of x squared plus 9. And if we square that, actually I'll write it out. So the square root of this squared, and then we are going to minus b squared, which is 3 squared, right? And that's all over this x squared times this square root of x squared plus 9 plus 3. If we go on to simplify, this power, the squared and the square root, will cancel out, so we'll be left with x squared plus 9. And if we do 3 squared, that will also be a 9, and this will all be over x squared times the square root of x squared plus 9 plus 3. And now we can notice that the top, the two 9s will cancel out, and we'll be left with x squared over x squared times the square root of x squared plus 9 plus 3. And now we can see that this function right here has these two common factors of x squared. So essentially we can cross them out and simplify the function even further. We'll be left with 1 over the square root of x squared plus 9 plus 3. Now that we've completed this simplification, right, there's nowhere else to go. There's no more like crossing out, no more simplifying anything, no more distributing. Let's test now if we can plug in this 0. So I'll bring this over here, and if we plug in 0 now, we will notice that it actually works, and we will not be getting a division by 0 error. So we'll have the square root of 0 squared plus 9, which is just 1 over the square root of 9 plus 3. And the square root of 9 we know is to be 3. So this will be 3 plus 3. And this will evaluate to 1/6. And now you can see that we've computed the limit. So this rationalization trick is pretty useful. A lot of the times it will come in handy when you see the square root minus something or plus something. So this square root minus something right here, this should be a big giveaway that we are going to use this little rationalization trick. So now for the last theorem, this is Squeeze Theorem. And I'll give you a formal definition, but essentially what we want to think of in Squeeze Theorem is literally compressing a function between two other functions. The definition goes along the lines of this. If f of x is less than equal to g of x, which is less than equal to h of x, meaning this g of x is kind of sandwiched in between f of x and h of x. And we also have this condition where the limit of the outer functions, they're both equal to this limit of L, then we can conclude that the limit of this middle function will also equal to L. It's very useful when we're dealing with I find trigonomic functions, that's where it's mostly asked. So I'll give a quick example and show you when we can apply the squeeze theorem. So if we're given a question like this, where it's asking us to find the limit as x approaches 0 of x squared times the sine of 1 over x, we can quickly see that direct substitution won't work because, again, we'll be getting a division by 0 error here. And we can see that no other tricks that we really know of, like simplifying a function, will work, or rationalizing a function will work either. The only thing left is to use the squeeze theorem as of now. And again, like I said, it's generally with these trigonomic functions that these are a decent indicator that we might have to use squeeze theorem. So the way squeeze theorem goes is we take this the trigonomic function, and we know that this sine function, the sine function always lies in between these two values. We know that the sine of 1 over x always lies in between these two extremas, which is -1 and 1. And now if we notice, we're starting to get this format right here. However, g of x right now, in order to apply this final then statement, g of x, it kind of needs to represent this because this is the limit that we're solving for. So we can get that extra x squared by just multiplying everything by x squared. So let's multiply the left side by x squared and the middle by x squared and the right side by x squared, because technically that doesn't change the equation because we were multiplying everything by this common factor of x squared. And now we can see that g of x right here in the middle is resembling the function that we have at question. And now we can apply this squeeze theorem. So let's check this these outer limits right here. So we have this function in the middle, g of x, which is sandwiched in between minus x squared and x squared. All that's left to do is ensure that it satisfies this property right here. So the limit of minus x squared as x approaches 0, we know that this is 0 because x squared is a polynomial function, and we know from the direct substitution that we can just plug the x value in if we're dealing with continuous polynomial functions which include this x value in their domain. In this case it does because x squared is continuous. So we can straight up plug x equals 0 into our function and find the value of our limit. Now let's check the other right side limit, the x squared. So the limit of x squared as x approaches 0, this right here is also equal to 0 because it's the same thing essentially, but non-negative. So it's a continuous polynomial function that includes 0 in its domain, so we can apply direct substitution and find our limit, which is going to be 0. And now we can see that this property right here, the one that I was talking about, is satisfied because both of the outer limits, they do end up equaling the same thing, and that means that we can conclude that the limit as x approaches 0 of x squared times the sine of 1 over x is also 0. because it's kind of sandwiched in between them and it follows this squeeze theorem. So I'm going to show you like a graphical representation of what we just did and kind of what the squeeze theorem is. So okay, I decided to use a graphing calculator for this because the x squared times sine of 1 over x is a little complicated to draw for me. But essentially we could see over here that the blue function is x squared times sine x of 1 over x. The red is x squared and the green is minus x squared. And if you see, this blue function is kind of getting sandwiched in between this upper red function, which is x squared, and this lower green function, which is minus x squared. And that's what the squeeze theorem is. We can clearly see from this visual that what the squeeze theorem does is it uses the fact that these two functions will keep this central function in between them. And at 0 right here, we know what the limit of x squared and minus x squared is. So because this middle function of x squared times sine x of 1 over x is in between them, it's sandwiched in between those two functions, we can also conclude that the limit of the middle function will also equal to the limit of the two outer functions. So that concludes my lesson on limits and a brief introduction on how to evaluate them. Hopefully you enjoyed the video. Leave a like and comment as to what it helped you. Also, if you are new to the channel, please like, comment, and subscribe. It is greatly appreciated. And yeah, I will see you guys in the next video.